of time for them. And so I encourage all of you that have questions to please, hopefully Roger's going to stick around for a little while, right, to meet up with him. And next we have Michael Murphy. And Michael has come here from Pendleton, and we are so lucky to have him too. He's from NOAA, and he's a climate leader there, and he's going to tell us all about what's happening with the National Climate Assessment.
Thank you very much. Again, yeah, I'm Mike Murphy from the National Weather Service in Pendleton. I'm happy to be here today to talk to you guys about climate and climate science. So just a real quick introduction. First, I'm going to be just taking a quick background look at the Earth's climate system. Then we'll be looking at some of the recent indicators of climate change going on around us. Then we'll look at some of the short-term outlooks, like seasonal outlooks. And then finally, towards the end of the presentation, we'll look at those longer-term impacts that we could be expecting over the next century or so. So the first thing we need to talk about is the difference between weather and climate. I know a lot of you guys probably already know this, but weather is more on a shorter time scale. Those are things like tornadoes, hurricanes, snowstorms. So sometimes you hear people say, oh, we had a big snowstorm, it's been really cold, you know, global warming's not happening. Well, that's not true. That's weather, that's not climate. And of course, climate is, again, the opposite of weather. It's a longer time scale, it's more statistical, and doesn't include those things like snowstorms or tornadoes or hurricanes. And looking real quick at the whole climate system, it's very complex. There's a lot of different interchanging parts and variables that go into our climate system. So this is important to keep in mind when we take a look later at those climate models. Just realize there's a lot of variables and a lot of things going on. It's not simple. So the climate models are getting better. They are using more inputs, so we're getting better and better at predicting the future of our climate and weather. And again, just some quick background knowledge here. We all know about the greenhouse effect. The Earth does have a natural greenhouse effect, which is actually very important to us because without this natural greenhouse effect, the Earth's temperature would be around 0 degrees Fahrenheit. So we'd be living on a giant snowball. So it is important that we do have some CO2 in our atmosphere, but as has already been mentioned here today, with the CO2 rising above 400 parts per million, it's some of the highest levels we've seen in tens of thousands of years, and that will have a profound impact on our climate. It already is having an impact, and definitely in the coming future. So talking about, real quick, just some of the natural climate variability. We do have, I'm sure a lot of you have heard about ENSO and El Nino, La Nina. These are things that impact our climate more regionally and on a seasonal time scale. So again, these are just some of the things you might hear people saying out there in the community that might not understand climate science. You might say, oh, it's been a cold winter, you know, global warming isn't happening, but it might have just been a La Nina winter. We tend to have colder winters when we have La Ninas here. So you're going to get that seasonal variability all the time when either you have a La Nina or El Nino. And then we also have something called the Pacific Decadal Oscillation. And the PDO, this is sea surface temperature of the Pacific Ocean have a large impact on our weather and climate here in the Northwest. And we got this PDO, might be a little hard to see, but when we have the cold or negative PDO, you're going to have some cold water along the west coast, colder than average water along the west coast. And then the opposite is true when you have the warmer positive days. We have the sea surface temperature anomalies above average along the west coast. And that, again, will have a large impact on our weather, and it's on a time scale of about a decade. So, let's see, yeah, when we have the negative PDO, we tend to be colder, especially on the west side of Oregon and Washington, but a lot wetter, as you can see up here in the middle. We tend to be a lot wetter during that negative phase of the PDO, and then when we're in the positive phase, we're a lot drier. So this is just trying to show you guys that there are different players, especially in the Pacific Ocean, that have a large impact on our weather and climate, even on a decadal oscillation. So currently we are in the positive PDO phase, and we have been since 2014. So, and again, the positive PDO, these are precipitation anomalies across the U.S., so we tend to be a lot drier in the Northwest with the positive PDO. And if we flip around to a negative PDO, we'll be a lot wetter. And this is a historical PDO index, and you can see it's highly variable and complex, just like the climate system is, but it tends to be on usually a 10 to 20 year period time change. And switching back to some of the indicators of a warming world real quick, yeah, we're definitely warming up. Global temperatures are rising, for sure, that is a fact. And these indicators are helping us to determine this. We're seeing rising temperatures over the ocean, rising sea surface temperatures, sea ice is decreasing, glaciers are decreasing, snow cover is decreasing. All the signs we'd expect to see from a warming world are indeed happening. So this just adds more evidence to those satellite and other derived temperatures that we have. Taking a real quick look at the greenhouse gases, we have different ones. A lot of people might not know that water vapor is actually one of the most abundant and powerful greenhouse gases out there. But again, that's the natural greenhouse gas that's keeping us at that more comfortable 57 degrees instead of that 0 degrees. So water vapor is important. And then we do have natural CO2 in the atmosphere, but as this chart shows over here, you see the red line is the historical carbon dioxide in the atmosphere, and clearly since about 1850 we've seen this CO2 level just skyrocket, and now we're actually off the chart above 400 parts per million. So there's no doubt that the level of CO2 is increasing, and CO2 does have a longer residence time in the atmosphere. I believe it's on the order of about 100 years or a little bit more. And then we do also have methane, which is a powerful greenhouse gas. It has very strong effects, but it is lower concentration. And methane, the residence time is shorter, on the order of decades instead of centuries like CO2. But it's still an important one to know about in the atmosphere. Looking at those temperature trends in the upper right-hand chart there, definitely see that upward trend and since the 1970s. And the lower chart is actually really interesting. I like this one a lot here. Might be a little hard to see, but in the green, these are the previous temperatures since 1900. I mean 2010 on this side, and in the green is what we'd expect to see if we had natural factors only. So we expect to see temperatures just kind of leveling off, staying about the same. But we include natural and human factors. The temperature curve follows that very nicely, which is a good indicator that humans are having an impact on global temperatures. And then again, a lot of that heat content is going into the ocean. We have about 93% of the heat from global warming is being absorbed by the oceans. And some of these charts on the other side are showing those global sea surface temperature anomalies, which have been positive or warming oceans since about 1995. And then, yeah, the lower chart shows the same thing, just adding more evidence to that. The oceans are heating up. And then we have that other signal, the sea ice. The sea ice has been decreasing rapidly, especially since 2000. Take a look at this chart up here. 2016 is in red, so we were down as about the third lowest Arctic sea ice year on record. And all the lowest years have come since 2000, with 2012 being the lowest, dipping way down about 3 million square miles, I believe it was. And that minimum usually comes in September for the Arctic sea ice. So, and in these dotted lines here, this is the 1990 average. You can see how far we've dropped even since the 1990s. And this gives an illustration. 2012, in September, we only had sea ice. In this area of the Arctic, this was all open water up here. So we are losing ice very quickly in the Arctic. And we're going to switch gears a little bit and talk more locally. you guys all probably remember 2 winters ago, 2014 and 15, Oregon had the lowest snowpack on record, as you can see on the right-hand side there. And this chart just shows Oregon snowpack since 1981. And again, 2 years ago was the lowest on record. And this could be kind of a hint of things to come in the future if we don't change. This is just a little more about that 2014-15 snowpack.
Mike? Maybe hold the mic closer.
Oh, sorry.
Drop that.
So yeah, this is the 2014-15 peak snowpack across
Can you
Oregon.
check your switch? It's switched off for some reason. Maybe it's not here, but.
At the bottom.
Oh.
Here.
Is that better?
Yes.
Okay. So yeah, this is the 2014-15 peak snowpack. And again, just reiterating the fact that we had 60 to 90% below typical peak levels here in north central Oregon. And the snowpack peak came 6 to 12 weeks earlier in the year. And some of the climate models, which we'll show later on in the presentation, are showing this might be a look into the future. So if you remember 2 years ago, that winter, that could be what we're going to be seeing as a typical winter towards the end of the century, or even sooner. So, and the summer of 2015 was also very hot. Just real quick, yeah, the global temperatures were much above average. And in the dark red here, Pacific Northwest, we had one of the warmest summers on record. We're very close to it. And this is just a regional look at that summer of 2015. So this was 2 years ago, not last summer, but 2015. We had well above average temperatures across all the Northwest. And then this is the precipitation anomalies. It was extremely dry too. We had some places less than 5%. I know some places didn't get any precipitation the entire summer. So very dry. And 2015 as a whole was, again, very warm, well above average temperatures, and below average precipitation through much of the area. And some of those snowpack trends, these charts are interesting here. The one in the upper right is the snow water equivalent observation since 1950. You can see the entire area. All the red circles indicate that we've seen a decreasing snowpack trend, and a lot of places have seen 60% decrease since 1950 on April 1st. And these are the temperature trends as well across the Northwest since 1950, at least 1 to 1.5 degree Fahrenheit rise. And you can see the chart here, again, temperatures rising since about the 1930s, above average temperatures across the Northwest. Kind of what we'd expect. And precipitation trends, a little bit surprising maybe. Much of the state has seen a 15% increase in precipitation since the early 1900s. But we have seen a change of earlier springtime peak stream flow by at least 10 to 15 days already, and that has a lot to do with the snowpack. And yeah, this is an important note too. The percentage of rainfall from heavy precipitation events has increased by at least 10% since 1980, so we're seeing more heavy precipitation events. And I want to take a really quick look. I found these charts here. These are actually just for Bend itself since 1900. There's a disclaimer on the bottom here that this is only representative of just one station in Bend. It's not representative of the whole Northwest. So there could be some errors, but this is from the Washington Office of the State Climatologist. And the annual mean temperature at this Bend station since 1900 has been about flatline. Really hasn't changed very much, but if you look at some of the shorter trends, you see we were kind of warmer earlier in the 1900s, and we had a cool period in the 40s, 50s, and 60s, and then we have been rising since about 1970. But overall, the annual mean temperature has not risen very much at this one Bend station since 1900. The annual average maximum temperature is actually trending slightly down since 1900 at this one Bend station. But again, if you look at the shorter term trends, we were warmer from about 1900 to 1930, and then we had a very cool period in the 40s, 50s, 60s, and 70s, and we've been rising since about 1975 here at Bend. Now looking at the annual average overnight low temperatures, this is where we do see a very distinct upward trend, about 0.1 degrees Fahrenheit per decade. So back in 1900, the average overnight low temperature for the whole year was about 32.5, and now we're up to about 33.5. And that's for the whole year again. Precipitation trends. We are actually trending down in our overall yearly precipitation at Bend. A little bit, we were around 14.5 inches, and our average is down just over 10 inches. So we've definitely seen a drop in precipitation here. But again, this is only that one station, so I just thought you guys would be interested in seeing Bend. The winter time temperatures in Bend have been rising slowly since 1900, with about 0.1 degrees Fahrenheit per decade rising. But our last really cold winter was back in about 1993, and since then we haven't really seen very many cold winters like we have seen in the past here. And we got that 40s, 50s, 60s, early 70s period was pretty cold here in Bend, so we've kind of gone up and down and back up. So, interesting trends. And for that wintertime maximum temperature, pretty much the same thing as the previous slide. Again, the last real cold winter was 1993. Since then, we've just been near to slightly above average. One of the warmer winters of note was back in 1934, at least at the Bend station. That was a pretty warm year for most of Oregon. And the overnight low temperatures in the winter have definitely been rising. One of the biggest rises here, at least 0.2 degrees per decade rising. And yeah, again, of note is we haven't really seen any really cold winters for those overnight low temperatures since about 1993. And that was the last year we've gotten down below 18 degrees. They used to be a lot more common back here in the early 1900s, a lot colder at nighttime. And we haven't really seen much of that in the recent past. And we'll skip through some of these. This is the wintertime precipitation, pretty flat trend. Now looking at what we had this previous year and this previous winter and this previous water year that just ended, we actually did a lot better compared to what we had in 2014 and 15. This is the Upper Deschutes and Crooked River Basin snowpack. Let's see, the black line, dotted line here is a normal snowpack, and the red line was this past winter. So the snowpack was a lot better off this year. We recovered pretty nicely, but we did melt out a little earlier than is typical. But overall, not bad this past year. And yeah, this is the April 1st snowpack across the whole state. And again, this past year, 2016, not too bad. We were right around 100% of average. So, and with that in mind, we are starting to do better. We did have a pretty bad drought back in 2015. Much of the state was in extreme drought, especially the eastern part of the state. But the latest update, as of September 13th, we are down. We still have some ongoing drought issues. Central Oregon is in just abnormally dry, but some parts of the state are still in severe drought, especially northeastern Oregon. But we are better compared to 2015. Really quick looking at some of the fire statistics across the state. Overall, the takeaway message here is that the Forest Services are always doing their prescribed burns and everything like that, so it's hard to really say how climate is affecting our wildfires season so far. This is according to the Oregon Department of Forestry and the National Interagency Fire Center. The length of the fire season, or the start of the end dates of the fire season on top here, have been pretty flat. Again, not much of a trend there. And same thing for the length of the fire season. Since 1977 through 2013, has had its up and downs, but overall the trend is pretty flat. So far we haven't seen the lengthening of the fire season. And currently, for this upcoming winter, we are expecting an end zone neutral condition. So they were earlier thinking it would be a La Nina winter, but now they're thinking it's just going to be borderline, if not neutral conditions. So for the upcoming winter, we're not seeing much of a climatic signal. So we're probably going to end up being pretty close to average this winter. And that's what the Climate Prediction Center is saying for temperatures this winter. They have us in the category called equal chances. So again, probably pretty close to normal. Could be slightly below average temperatures, could be slightly above average, but not expecting too much of a trend for the winter. And as far as precipitation goes for this upcoming winter, Central Oregon is on the edge of the above average precipitation, but still officially in those equal chances, so probably pretty close to normal, could be leaning slightly above average for precipitation and perhaps snowfall for this winter. But we're not expecting the driest year on record, we're not expecting the wettest year on record, just pretty average probably. Okay, looking further ahead into the future, we have certain climate models that they're becoming higher and higher in resolution, and they're going out further, to the year 2100 at least, even some go out further now. And it's really hard to see, but over here this chart is just showing that they're now taking into account a lot more things. Back in the earlier years in the 90s, they only had the land surface and the ocean and sea ice, but now we have a lot more vegetation and atmospheric chemistry and land use. So they're adding more and more variables into these climate models. They're getting better and better, higher resolution, and I think they're going to have some pretty good outlooks here for us. So some of the different scenarios that these climate models are predicting, we have what's called the representative concentration pathways, or RCPs, and there's at least 4 different ones, the main ones. We have RCP 8.5, and this is a scenario where it's just business as usual. We keep producing CO2 and emissions, and we don't really do any change. Again, that's going to be the RCP 8.5. And 8.5 stands for increasing the solar input 8.5 watts per meter squared by 2100. So just know that's the business as usual scenario. And then we have these different ones, RCP 6, and this is kind of stabilizing our emissions by about 2050 and kind of leveling off. And then RCP 4.5 is stabilizing our emissions sooner and leveling off by 2100. And then RCP 2.6 is if we made drastic changes now and cut our emissions back very quickly, and we actually had lower emissions in the year 2100 than we have now. So that's kind of the best case scenario, the RCP 2.6. And this chart over here on the upper right shows those different fossil fuel emissions I was talking about, and it gives you an idea of kind of what I was just saying, how 8.5 is in red and just our emissions just keep increasing, whereas 2.6 we already have our peak in emissions right now and actually dropping off by 2100. So there are a lot of uncertainties in these climate models still, even though they are getting better, but excuse me. But the RCPs themselves are actually a large source of uncertainty because we don't really know what society is going to do. We can try to decrease our emissions, but these are only 4 scenarios, so there could be other scenarios we just don't know. That's a source of uncertainty right there. And then, again, as I said earlier, they're trying to add more and more variables into these climate models, but you can't model everything. There's going to be little changes, like the saying goes, if a butterfly flaps its wings in Brazil, it affects the weather here. So there's going to be all these little changes that we can't get into the climate models just yet. We're getting better and better, but we can't have everything. And then there are these model feedbacks, which they are starting to account for now. Cloud cover is a big one. We're not exactly sure how cloud cover is going to affect the future climate. The models are getting a better handle on that, but that is a big area of uncertainty. So with that in mind, these are some of the best projections from these climate models of global average temperatures. The lowest scenario, which would be that RCP 2.6 I was talking about, where we cut emissions quickly in the very near term. That's going to put us, even if we cut emissions right now to lower levels, we're still going to be about 1.4 degrees Celsius warmer by the year 2100, according to the climate models. And if we continued on business as usual, we don't try to cut emissions at all, we just keep emitting, that's going to put us at least 4 degrees Celsius, or almost 8 degrees Fahrenheit, above where we are right now by 2100. Okay, and then another important note is that with these increasing temperatures, we're going to see a shift in the overall climate. So we're going to see warmer temperatures, and that's going to mean the whole climate. This was our climate right now in the dotted line. It's going to all shift warmer, so we're going to have less cold weather. Our average temperature is going to shift warmer this way. We're going to have more hot weather and a lot more record hot weather. It's just kind of shifting. And these are some of the regional projections here. Again, it's very likely that we're going to warm up in the coming century regardless of whether emissions decrease or not. But most of North America will see an increase in precipitation, which is kind of interesting. Let's see, so yeah, these are the different RCP scenarios I was talking about, and this is the temperature change. So RCP 2.6 is in the upper left there, just minor change, about 3 degrees, up to 3 degrees Fahrenheit. But you can see the worst case scenario here, RCP 8.5, shows dramatic warming across all of the United States on the order of 8 to 15 degrees by 2100. And then taking a look at the precipitation here, again, this is a lower best case scenario where we cut emissions right now. We're going to see a little bit of an increase in wintertime precipitation over the Northwest. In the summer and fall will be about the same. But with that worst case scenario, the 8.5 business as usual, we'll see a large increase in precipitation in the Northwest in the winter, and then the summer will be a lot drier actually. So that'll probably have profound impacts on our climate, seasonal climate here, with wetter winters and much drier summers.
Lower snowpack.
Lower snowpack, yeah. Then I found this report here very interesting, to me at least. So here we are, these are the number of 100-degree days. So this first one here is the recent past. You can see all of Oregon averages less than 10 days above 100 degrees per year. I think down in this area, it's probably just maybe 1 day at most of 100 degrees, or probably even less at Bend, maybe Redmond, 1 day per year. Then up towards the lower Columbia Basin of Washington, Oregon, it's probably the average maybe 3 or 4 days above 100 per year right now. But with the lower end scenario, even the best case scenario, we're talking about the RCP 2.6, the best case scenario still has our area seeing an increasing number of 100-degree days. That lower Columbia Basin seeing 20 to 30 days above 100 degrees by 2080 to 2099. And it looks like, look really closely, some of that sneaks down towards Redmond. So it might be more like 20 days above 100 at Redmond, even with the best case scenario. And then the worst case scenario is actually very scary, to me at least. That would put the lower Columbia Basin at 60 to 75 days above 100. So basically the entire summer would be above 100 degrees for the Tri-Cities in Washington, Hermiston, Oregon, almost every day above 100. And even down here, it's kind of hard to see, but it's about 45 days, 30 to 45 days above 100 degrees. And that's with the worst case scenario. So I think that's something to really look at, because with that many days above 100 degrees, that's going to affect people that work outdoors quite a bit. So I'm going to keep that in mind. And yeah, this chart is more on precipitation here. All of North America is actually expected to see an increase in maximum precipitation. This is kind of what I showed before. So Yeah, with the best case scenario, we'll just see a slight increase up to 10% of precipitation for the whole year. But with that RCP 8.5 scenario, we're going to see a more increase in precipitation, but at the same time, we're going to have much drier in the summertime with more consecutive dry days. So we're going to see more rain in the winter, and then it'll just dry out in the summer, and we're not going to see much in the summer. You have a question?
Can I ask a question? Yeah, you keep saying we. Does we mean North America, or does we mean reduce emissions for the whole world?
The emissions, the RCPs are based on the whole world.
Okay.
Yeah. Mhm.
Thank you.
Yep. But yeah, when I say we for this chart, it means just the Northwest. You can see we're going to be more consecutive dry days. And yeah, more precipitation trends, more seasonal trends here. This is just that higher emissions scenario. And again, much of the same, still showing that was decrease in precipitation in the summertime by as much as 20 to 30% at least. And the bars indicated statistically significant, so it's pretty good. The models are really showing that trend for drier summers here, and at the same time wetter winters. So you have to look at the different seasons. Overall, we're going to see more precipitation, but at the same time, you might have more summertime droughts and harder for agriculture that needs that water. And this is showing some of the changes that are already happening. You've probably seen in the news quite a bit, actually, this year. We are seeing a lot more very heavy precipitation events across the United States, especially in the northeast and eastern part of the area, but even out here in the northwest. We have seen about a 12% increase in very heavy precipitation events here. But across the northeast, they've seen 71% increase. So that's why we had like those West Virginia floods, and then the floods down in Louisiana. These are going to become much more frequent in the coming future, according to the models. Not so much of a change for us so far, but definitely the eastern U.S. And this was very interesting here. This, I believe, is based off the RCP 8.5, so that higher emission scenario, kind of the worst case scenario. But the colder days, this would be the coldest day of the year in the winter. If we have this RCP 8.5, it's going to be as much as 10 to 15 degrees warmer than what we've seen in the past. And same thing for the hottest day. So whereas in the recent past, we may have seen the coldest day of the winter in Bend to be -5 degrees, say. Now we're expecting to be more like 10 degrees would be the coldest temperature of the whole year. And then same thing for the hottest temperature, where it may have been 95 or 98, it would now be like 108 degrees in Bend in the summertime. This just shows the projected change in soil moisture. And again, those two different scenarios, the higher emissions and the lower. The overall takeaway is soil moisture would actually increase. This did not do it by season, this was just for the whole year average, so we probably had that trend, but overall we'd see higher soil moisture, but probably lower in the summertime still. And this just breaks it down a little bit more for the Northwest, as far as temperature and precipitation anomalies in the coming years. So, and yeah, we have the lower emission scenario average and the high end. So by the 2020s, anywhere from 1 to 3 degrees warmer, 2040s, 1.5 to as much as 5 degrees warmer, and by the 2080s, the best case scenario is about 3 degrees warmer, and the worst case is almost 10 degrees warmer. And precipitation is not changing too much, but it was harder to, the models weren't as statistically significant for precipitation, kind of staying unchanged, but a lot of them, again, lean towards slight increases in precipitation, especially with more emissions. And then something I really want to talk about is definitely the change in the precipitation type across the Northwest. And that's what this chart does here. It shows the historical precipitation type. We have In the green color, it's going to be rain dominant precipitation. And then in the red would be rain and snow transition. So sometime of the year you get rain, in the summertime, other times of the year you get snow. That's what the red means. And then the blue is snow dominant, where more than 50% falls as snow throughout the year. So right now, historically, a lot of Oregon falls in that transition zone. We get rain in the spring and summer, and we get snow in the winter. Everything's good. But by the 2020s, it starts to change. We're already starting to see those changes now, very recently. And by the 2040s, a lot of Oregon changes to rain dominant. And by the 2080s, the entire area, except for maybe the Wallowa County mountains, are going to be rain dominant precipitation type. So a lot more rain instead of snow. And with that, we're not going to see the snowpack build up. It's going to be melting out earlier. And the stream flow is going to be occurring earlier, which is what this chart shows here. Yeah, so the summer stream flow is going to be reduced by more than 50% in some areas, and the runoff is going to be decreasing too. This is the summertime stream flow. You see the whole area is expecting decreases in runoff, especially on the west side. Very significant decreases over there. And really quick, a little bit more about the wildfires, since that's very important to our environment here. These are the projected increase in acres or areas burned through 2100. I'm not sure, but yeah. So you can see in the Blue Mountains and the Wallowa Mountains, we're expecting perhaps as much as a 500 to 600% increase in area burned in the coming future. And same thing along the Cascades, or not the same thing, 400, 500%, but same trend. And we are possibly going to see more insects and disease moving into our forests as well, as temperatures get warmer. And like I said, the coldest temperatures of the year are going to be rising too, and that's going to allow different species of insects to survive the winter more often and damage our trees more. So just some conclusions. You got the temperature going to rise between 3.3 to 9.7 degrees by 2100 based on the climate models. Annual precipitation is going to either increase or decrease between 10 to 18%, so less of a signal on precip. But a 10% reduction in summer precipitation is likely. There's virtual certainty that extreme cold days and nights will be warmer and occur less often. There is virtual certainty that extreme hot days and nights will occur more often. And it's very likely that the frequency and duration of heat waves will increase. We talked about that. And again, this heavy precipitation events might occur more often, but then we're going to be drier in the summertime. And that's why we're expecting drought will increase in duration and intensity. So a pretty complex scenario, but hopefully that all kind of makes sense to you guys. And yeah, that's all I have, just my sources and references.
About 5 minutes of questions.
Okay, yeah, thank you, and if I have any questions.
So where are all the climate refugees going to
What was the question?
go? Where are all the climate refugees going to go?
I don't know the answer to that one, so.
That's the problem, isn't it?
Yeah. Question over here?
Yes, they had an article in the newspaper the other day about dams being a big source of CO2 increasing. And how many dams we are putting in. Is that because of the water vapor you were talking about?
Actually, haven't heard about that yet. So they're saying the dams are creating more CO2 in the atmosphere?
Yes.
Reservoirs. It was methane.
Oh,
trees.
I'm not exactly sure. Must be something they're using.
It's a recent discovery or a recent realization.
Okay. Sorry, I don't know too much about that. But,
Mine's really quick.
okay.
Is your PowerPoint available online somewhere?
I can make it available.
That would
Yeah.
be super.
Can set it up with
We'll have those available
Wonderful.
to the extent we can.
Go to the back here.
Yeah, just a question, since rainfall precipitation varies around Bend, where is the weather station yours was based on? Because I was struck by 14.5 inches 100 years ago, 10 inches now. That's quite a change. So where was that station?
I believe that was on the kind of the southeast side of Bend, but it's somewhere right in the city of Bend. So
Yeah, well, but was it, I mean, we're in a rain shadow here, so the climate changes as you go east in the city itself, so it's in the east side.
I believe so. I'd have to look at, again, that's from the Washington climatologist. I had to look at which station they use exactly. It's probably either the airport or one of the co-op stations in Bend.
I was really struck by the slide that showed the increased temperature scenarios in the 1900s to 1940, and it looked really similar to kind of the variation we're seeing now. Did climate scientists have an explanation for what caused that warming trend, and how does it differ from the warming trend we're in now?
That's a good question. Let's see.
I know you weren't born.
Oh yeah, she was asking, she's noticed the trends in temperature were upward in the 1930s, and then they were similar to what we're seeing right now, and she wanted to know what the explanation for that was.
I think that might have been World War I. I know one of the scientists said had something to do with the war industry that created one of those unusual blips.
It was probably more,
But I'm not sure.
the 30s and 40s was probably more natural variability, could have been that PDO. I'd have to go back and look and see what the PDO was, but we saw more natural variability, and then we had the Dust Bowl in the 30s too, so I know that affected a lot of areas, so that's why probably 1934 was one of the warmest years. Yep.
I saw one picture that showed Florida half underwater, and I wondered if sea level rise is one of the things you can predict most accurately, or is that a variable?
Yeah, sea level rise is a big part of that. I was limited on time, so I left that out in this part, but in the evening session, I'll be talking a lot about sea level rise too. That's definitely been rising, and we're seeing more nuisance flooding already in sea level rise.